right. Okay, so we're doing the digestive system, and again, usually I have 5 lectures for the digestive system, and it's like, okay, we don't have enough time in this semester. And I really love teaching about the liver and alcohol metabolism, but this semester was like, well, do I talk more about immunization and virology, or do I talk about the liver? So the liver, I guess, had to be put on the shelf for this semester. But again, we're going to get through the rest of the digestive system. I know it seems very fast, but again, we're running out of time. There's like just barely over a month left in the semester. All right, so chemistry. I know how much you all love chemistry, right? So again, like if you need a break from chemistry, don't worry, this will be up on YouTube. And yes, it takes time to go on YouTube. I will upload Monday's lecture. So bicarbonate buffer system. So again, we did cover this in the cardiovascular system, so it does come back. Especially with the digestive system, if you don't understand the system, you don't know how we make these acids and neutralize these acids in your digestive system. So here we have carbon dioxide and water, and over here, this compound right here is carbonic acid. So remember, when acids are dissolved in water, they dissolve into their conjugate base and they release an acid. The acid protocol or acid particle is this hydrogen ion or proton. So this is acid. Again, pH acidity is determined by the concentration of hydrogen ions, the protons. All right, so here we have our gastric epithelial cells. Again, gastro, G-A-S-T, that refers to the stomach. So you have all this hydrochloric acid in there. Remember those parietal cells? So then remember that chyme, that acidic mixture of food, water, and gastric acid, that is chyme. It's very acidic. So what prevents your stomach from digesting itself from the inside out? Well, you have this chyme. So again, you have that mucus layer. So that forms a barrier that prevents the diffusion, slows the diffusion of hydrogen ions across and attacking your epithelial cells right here. All right, so hydrogen ions, but there's not only that. The thing about your mucus and your gastric mucus is that it also has bicarbonate ions. So this is why you need to know that bicarbonate buffer system. Because remember this bicarbonate buffer system, so you can combine carbon dioxide and water to form carbonic acid and then form bicarbonate and hydrogen ions. But remember, this is an equilibrium reaction. It can go both ways. So again, when you're combining carbon dioxide and water, you're forming this, but it can go the other way around. So again, what it can have is combined bicarbonate plus, again, protons, and then, again, that carbonic acid intermediate, but I'm just omitting it for simplicity's sake. So you can combine bicarbonate and hydrogen ions to form carbon dioxide and water. So carbon dioxide and water versus hydrogen ions do not affect pH directly. So again, this is how you're able to neutralize it. So not only do you have the mucus forming a barrier, physical barrier against the acid in your stomach, you also have bicarbonate ions that help to neutralize any protons, any acid ions that happen to diffuse into mucus and prevents it from actually reacting and dissolving your gastric epithelia. All right, so then we have our duodenal epithelial cells. So remember, right after that pyloric sphincter opens, releasing chyme into the duodenum, you still have that chyme. It's still very acidic. So the duodenal epithelial cells, thank goodness they have mucus. Again, you don't want your duodenum being digested as well. Why? Because you can also get ulcer there as well. So not coincidentally, you also have bicarbonate ions in the mucus of the duodenum. So this is how you're able to neutralize acid in the chyme. Chyme doesn't stay acidic all throughout your small intestines. Again, you have all this bicarbonate that helps to neutralize that digestive food so that it becomes less acidic as it travels further in your digestive system and your intestines. So again, you have bicarbonate reacting with acid to neutralize the acid, and then it generates relatively harmless carbon dioxide and water. All right, so this is why we need to talk about acid-base balance. Again, acid referring to proton concentrations and base referring to the opposite. So saliva, depending on conditions, it has a pretty broad, relatively broad pH range. So it can range from slightly acidic to slightly basic. Do I want you to memorize these specific values? Not really, because many different textbooks have slightly different values. It's around this. So tends to be neutral-ish, a little more toward the acid side on average. But the thing about saliva, it's also bicarbonate buffered. It's not just pure water. It also has some bicarbonate ions to help neutralize acid. And gastric acid, so again, very acidic. Why? Because of that very acidic hydrochloric acid. That releases a lot of hydrogen ions into the environment. So this is why gastric acid is super, super acidic. And then you also have, so think about this, again, you have your GI tract, your alimentary canal is all connected. So what prevents the acid from here digesting up here in your esophagus and also here in the duodenum? So remember, you do have those sphincters, you do have those physical barriers, but the thing is that your duodenum also secretes bicarbonate to neutralize any acid that happens to make its way past the pyloric sphincter. And again, your saliva is also bicarbonate buffered, so it's also going to neutralize any acid that happens to bubble up and burp out through your mouth. So again, this is how you keep your acid where it is. Not only do you have the sphincters to keep it in the stomach, you also have chemical buffers that help to keep the acid where it's supposed to be in the stomach, so you don't digest the rest of your GI tract with your gastric acid. So digestive enzymes and pH. So you have salivary enzymes, amylase and lipase. And the thing about your digestive enzymes, so they, just like you might function better in a very air-conditioned room, or maybe you like to study out in this when it's very, very hot. Your enzymes are very similar as well. They have optimal conditions where they function best. So, and digestive enzymes. So remember, pH involves those protons, and those do have a positive electric charge. But remember, your enzymes are mostly proteins, right? So then these proteins also have charges on them that helps them stick together. If you throw a bunch of acidic, hot, positively charged protons onto them, then these proteins can fall apart. So the thing about these enzymes, they have specific ranges of pH that they operate best at. Just like you have certain conditions you operate best at, like not having online class. But again, this is like salivary enzymes also have optimal conditions. So enzymes, salivary enzymes, not coincidentally, work best at the pH in your mouth. So you have these amylases and lipases, but what happens about gastric enzymes? Okay, so again, remember your gastric acid is very acidic. So these proteases like pepsin, they work at very acidic pHs. And same with duodenal and pancreatic enzymes. Remember, stomach acid very acidic, but you have a lot of base and bicarbonate here to neutralize that acid. So then you have amylases, lipases, and nucleases, and these work best at that slightly. Again, it's not completely basic, but again, compared to your stomach, your mouth and oral cavity and your duodenum and intestines are relatively basic compared to your stomach. So here we have a salivary enzyme. Again, it's very happy. Why? It's in its native environment. It's most comfortable there. It's going to be operating most efficiently in the mouth. But again, everything gets washed down. That bolus, that saliva and food mixture ends up going to the stomach. So the salivary enzyme, now it's moved from a very relatively basic pH to a very acidic pH. This enzyme is, again, most enzymes are proteins. This enzyme is going to fall apart and denature. If it's falling apart, it's not going to work. So the salivary enzyme is inactive when it actually hits the stomach. Actually, there is an exception. Lingual lipase is kind of unusual in that it actually functions better at this pH. So it actually stays inactive here, it does have some activity, but actually hits its stride more when it hits the acidic pH. But I think that's more of a 300 level question. I just want you to know lingual lipase exists. So then you have gastric proteases. You also have lipases as well. So you actually have a double whammy, gastric lipase and lingual lipase working together. So you have proteins and lipids being digested in the stomach. And these enzymes, again, work best in their native environment. But what happens when you shift them to a pH that they don't like? Well, they can denature or they can become less active, so they don't function as well. So again, this is why you produce certain enzymes at certain places. They, again, remember, different parts of your GI tract have different pHs, so it makes sense that you have different sets of enzymes that work best at different sets of pHs or different ranges of pHs. All right, so pancreatic enzyme, very happy because why? It's in its native environment. I know, I can't wait to go back to school and teach in the classroom again, but I digress. All right.